Okay, so once we define the square, the basis, we're more or less off to the races. Probably the most important slide of this presentation then is this middle slide, technological uncertainty. For those who want to follow along in the course handouts, it's pages B15 and B16. So if we can assume that we're thinking outside the box, or what the government would call, we've shown a departure from standard practice, meaning we've defined standard practice and we've quantified an objective that goes beyond it. If you read their various interpretations, that's ultimately the two key things that they're looking for. The next is they say you have to show the presence of a technological uncertainty. So obviously we're saying, well, okay, what is that? And what is it not? Fortunately, the CRA goes on to define it. They say that technological uncertainty can occur in either of two ways. The first is scientific uncertainty. They say, quote, the taxpayer is uncertain whether the goals can be achieved at all. No one's ever done this before as far as we know. That's great, but I would say that's less than 1% of the industrial R&D that we see being claimed successfully every year. The vast majority aims at the second type, or what they call system uncertainty. So they say, quote, the taxpayer may be fairly confident the goals can be achieved, but uncertain which of several alternatives, for instance, paths, routes, approaches, equipment configurations, system architectures, circuit techniques, and so forth, will either work at all, so there's your scientific uncertainty, or meet desired specifications, or cost targets, or both of these. Okay? So the CRA is saying that cost reduction could be a basis of uncertainty. Cost reduction while maintaining performance. Hey, I want to reduce the cost but not have any decrease in performance. Often those are the kinds of variables that we're looking at. I like to think of system uncertainty as integration uncertainty, as a layman's explanation. The Canada Revenue Agency has kind of a wordy explanation that basically says that. They say, quote, at the bottom here, work on combining standard technologies and devices is eligible if non-trivial combinations and principles for their integration carry some type of uncertainty. And so you read that and you say, what? And what they really say is, let's say I'm a machinery developer, and I've worked with servos, and I've worked with chain drives and belt drives and every kind of drive you can think of. But now I'm designing a machine where I have different issues on the motor and drive selection, which then creates spacing issues and electrical noise issues, which cause me to reevaluate my power requirements, which then cause me to go and change the layout or the footprint for vibration or electrical noise or any number of reasons. So a system uncertainty is a change in one component that creates an unpredictable upstream or downstream effect on another component. The easiest way to think of it is that if you have a model of a solution, maybe a chemical analysis, if I put x plus 7y plus 4z of this material in here, I'll get the final component. And if I vary x a little bit, or the characteristics vary, how's that going to affect y or z? If I have a formula that tells me, that would be standard practice. If I say, well, the formulas that we have tell me one thing, but the reality is something different, now I'm going beyond standard practice. All right? All right, so if you understand technological uncertainty, usually it's very easy then to determine what's the eligible cost that I can claim for the project. And the way that I like to define the technological uncertainty is to say not only what's the problem in a sentence or two, but if I were to develop a test matrix of things that I'm varying, what are the variables? So in a molding example, I may vary the heat that I'm using, the temperature that I'm using. I may vary the pressure that I'm using. I may vary the content of the mix as 3 variables there. 3 variables tends to be my magic number, or the CRA's magic number. If you're only varying one thing, I'm doing heat treating and I'm just going to vary the temperature up or down. The Canada Revenues say, well, you start with an ASTM standard and you just tweak it up or down a little bit. They'd liken that to tuning a radio. If I say, go to station 102.3, you may overshoot a little bit and go to 102.4, and you may go back to 102.2, but eventually, if you spend enough time, with absolute certainty, you will be able to tune into the station. Okay. So if there's only one variable, they don't consider that experimental development. If instead I say, well, you know what, I got to do 10 tests for temperature and 10 tests for pressure. But if I can argue, if I vary the temperature, then the optimal pressure would vary. How many people think I have 20 tests in my design of experiment matrix? How many people think I might have 100 tests? For each of the 10 temperature tests, I have to test pressure 10 times. So technically, I have 100. So if I add a third variable, like the amount of glass fiber in the mix, another 10 tests, now I have potentially 1,000 tests in that matrix. And I find that those 3 variables, X, Y, Z, or more variables, some clients have 18, 20 variables. Beautiful. 3 or more variables of uncertainty, where a change in one will have an unpredictable upstream or downstream effect on the others, is the magic number for the CRA. If they see 3 or more variables, they tend to say, okay, let's go on to the next step to see what these people did about those variables. Okay, so if the team can do that, what I like to say is that any time any team member says, hey, I think I did something, I did 5 prototypes here and it helped us answer 1 or more variables, that would be experimental development. So what we find is that once the problem is defined, the rest of it becomes fairly easy. What tends to happen is we get together as a team, we say, hey, look at this new project, what are we going to do about it? Within 15 to 20 minutes of that first meeting, the team defines the square and the triangle. Hey, that's like the X7 project we did before, but different in some ways, or we wouldn't be talking about it. If we tend to go ahead, we're probably going to have these kinds of problems because we're expert in the field and we know we have a heads up on what's coming and why we haven't done it. And we'll decide to go ahead or not. And then it's, Doug, you do this, Susie, you do this, Bill, you do this. We'll meet tomorrow, next week, next month, and figure out what we each did and go from there. So what I like to do is empower each of the investigators to basically be able to tell me what they did and learned in relation to each of the uncertainties, or any of the uncertainties. So if someone thinks they did something that allows them to answer or gain more insight on any of the variables of uncertainty in question, what we say is there's really 3 main ways to do the work. And because of the conciseness required of the project descriptions right now in a new format that we're going to talk about, we want to cut right to the chase. We want to tell the Canada Revenue Agency reviewer a couple things. The first thing that they'll be looking at is, did you get the answer on the first try? Hey, here's our problem, we did this and it worked. Does anyone see a problem with that? If you can get lucky once in a while, I'm not saying it's always going to be a problem, but if you say, here's my problems and everything that you're doing is getting it on the first try, there's a strong tendency that the Canada Revenue is going to come back and say you're either really, really lucky or your level of standard practice, your square, is bigger than what you think, which is why you knew the answer. You didn't have to do any experimentation. There was no experiments. You just developed the answer. So again, how many different alternatives did you look at? What were the differences? Get people thinking about that. And what I found is not only how many different ones, 5, 50, 500, if they were different, why were they different? Why did you need 50 or 500 instead of 5? And if you can support that, again, we're going to be on the basis where the CRA will be able to do what they call a desk review. They'll be able to say, hey, we've answered all our questions to a reasonable degree that we don't have to do a site visit. The next thing that I've found is not only how many alternatives did you look at, what method did you use to do that analysis or investigation? And what we found is there's 3 main methods. Each takes progressively longer than the last. So my first method of experimentation is what I just call analysis or simulation. I think of 12 ideas and I analyze them on my computer. And maybe each one takes an hour, for argument's sake. And maybe out of those 12, I say, well, there's 3 that show particular promise based on my analysis. So now I'm going to take those 3 ideas and I'm going to go on the shop floor and I'm going to get the machinery guys, all 20 of them, to recalibrate the machines and run some process trials through and analyze some of the variations that I've simulated in step 1. So instead of maybe 1 hour per test there, it may take 20 to 30 man hours. I've got all these guys here. We've got to reset machines. We've got to set them back. 20 people involved. So it's going to take progressively longer. And then the last level, stage 3, is typically where we go through and we determine, no matter what we try using our existing technology or machinery, I don't think we can tweak this enough or develop it enough to meet the objectives. I think we have to start all over from scratch with a complete new prototype. And then usually there's a 3A and B, because you generally don't tend to get it on the first try. You may revise it 5, 10, 15, 30 times. So there's how many complete prototypes did we do and how many revisions to this prototype. So the first type of work tends to take hours, the next tens of hours, the third section hundreds, often thousands of hours. And what I found is the reviewers are skilled enough that if they understand more or less what you're doing and you provide them with this, they can make a fairly informed decision on whether the 3,000 man-hours you claimed is reasonable or if they need to come and review your documentation to understand exactly how that went. All right? Okay, so if you understand the basis of that, that we want each of the investigators, I call them, primary investigators, to be empowered to say, hey, I think I've done something at some point that helps our team answer one or more of the variables of uncertainty, to tell us just briefly how many alternatives that they looked at, the method that they used, what the results were, how did this tie to our original performance, any objectives, did we get closer, were we further, how close to the objective did we get, and in addition to the results, the conclusion. So the result is what actually happened. Well, I was aiming for $97 a unit from 100 and I got to $94 a unit. I exceeded expectation by 100%. That would be the result. The conclusion would be why. Can I explain why I exceeded my expectations by 100%? Obviously, I didn't predict these things well enough or I wouldn't be out by 100%. And the more things vary from expectation, the more likely there is a potential conclusion, which ultimately is the technological advancement that the government's looking for. So the whole picture, what they call the realm of experimental development, has those three components. A thrust beyond the knowledge base, so thinking outside the box, definition and agreement with the team of at least one or more technological uncertainties, more importantly the variables of uncertainties, at which point any of the investigative activities that are performed in Canada by taxable suppliers, and we're going to talk about those, would be the basis for our claim.